Students, in this video we are going to discuss about maximum power transfer theorem. Here is a statement. Maximum power will be transferred to the load by a network if the load impedance is conjugate of the network impedance. So given a network with network impedance ZS, then this network can transfer maximum power to the load when load impedance is complex conjugate of your source impedance. So given a network, the first step is to find the Thevenin's equivalent circuit, so that you find one voltage source in series with one impedance for that particular given circuit, and then we can find the value of the load impedance by taking complex conjugate of this source impedance. So this particular load impedance, if you are going to calculate by this formula, then the load will get maximum power from the network. If it is going to be a DC circuit, then load resistance value should be equal to source resistance for maximum power transfer. So let me demonstrate this maximum power transfer theorem using a circuit. So here is a circuit. RL is the load resistance. We are going to calculate the value of this load resistance for maximum power to be transferred to this load. So since this is my load, I will mark AB across it. So the first step in maximum power transfer theorem is to get a Thevenin's equivalent. In Thevenin's equivalent, let me compute first the Thevenin's resistance value. To get Thevenin's resistance, the first step is I should remove this load resistance from the circuit. Then I should kill the source involved in the circuit. So after removing this load from the circuit, I will get a circuit like this. So in this circuit, I have removed the load, and I should also remove this 10 volts. So the voltage source will be removed from the circuit by short circuiting, which means that these 2 points, this point and this point, has to be short circuited. So I am giving a short in between like this. So to find the resistance across AB, let me pump in a current here. So the pumped in current will get divided into 10 ohms and 15 ohms current. Both of them will get shorted here or meet here, and then get divided into two branches again, one to the 25 ohms and another one through 20 ohms. So I will redraw this for the better understanding. So we can draw this as two parallel sections, that is 10 ohms in parallel with 15, again a short here, and then 25 ohms in parallel with 20. So resistance RAB, or otherwise called as Thevenin's resistance, is obtained by 10 parallel with 15, which means 10 into 15 divided by 10 plus 15, plus 25 in parallel with 20, which we will get it as 17.1 ohms. The second step is we have to find the VOC, or Thevenin's voltage, that is voltage across open circuited terminal AB. So which means that I have to remove this load from the circuit. So I'll get a circuit like this. So now load is removed from the circuit, and we have got to find out voltage across AB. So to find voltage across AB, if you look at the circuit, from A to B, if I travel across AB, you can see 15 ohms and 20 ohms are getting connected, or the other path you can take it as 10 ohms and 25 ohms. So if you find voltage drop across 15 ohms and 20 ohms, that will be enough to find voltage across AB. Or you can find voltage across 10 ohms and 25 ohms, so that put together you can find voltage across AB. So any two elements you can select. Let me select 15 ohms and 20 ohms. If I know the current through this 15 ohms and 20 ohms, then it will be easy for me to find out the drops across 15 ohm and 20 ohm. So from this circuit, you've got to find out what is the current flowing through this 15 and 20. So from this 10 volt supply, a current I will be pulled, so which will flow like this, and coming to this point, the current will get divided into two, I1 and I2, and this I1 will flow through 10 ohms, 15 ohms, and it will get grounded. Similarly, I2 will flow through 25 ohms, 20 ohms, and it will get grounded. Which means in this circuit, this 10 and 15 both are in series, 25 and 20 are in series, because same I2 current will flow through 25 ohms and 20 ohms. So, but this section, that is 10 plus 15, will be in parallel with 25 plus 20. That will be the total resistance involved in this circuit. Now let me find the current I. So the current I is nothing but I is equal to 10 divided by R total, where R total is, this is 10 plus 15, both are in series, isn't it? So 10 plus 15 is 25 in parallel with 25 plus 20, that is 45. Which you will get it around 16.07. That is 25 into 45 divided by 25 plus 45 ohms here. Now I is equal to 10 divided by 16.07, which comes around to 0.62 amps. By using current division rule, you can find I1 and I2. So I1 will flow like this. So this is entering terminal, leaving terminal. Here again current entering terminal and leaving terminal. Similarly, I2 will flow through 25 and 20. So current entering terminal positive, current leaving terminal. Here also current entering terminal and leaving terminal. So the current I1 is equal to the total current entering at this point, that is 0.62 into the opponent hand. That means this hand contains 45, opponent hand resistance divided by 45 plus this hand, that is 10 plus 15, which is nothing but 25, which will come around to 0.4 amps. Similarly, I2 is nothing but the total current 0.62 into the current is in this branch now, that is 25-20 branch. The opponent branch is 10 plus 15 branch. So 0.62 into opponent branch is 25. Opponent branch resistance is 25 divided by 45 plus 25, which comes around to 0.22 amps. Students can note that I1 is 0.4 amps and I2 is 0.22. Put together, I1 plus I2 will be equal to 0.62, that is I. Now you can find voltage across AB, that is voltage across AB is equal to, I will now travel from this A point to B point. I come here like this. So plus minus, so plus 15 into what is the current here, 0.4, isn't it? So plus 15 into 0.4 will be the voltage drop across this 15 ohms resistor. 15 into 0.4 will be 6 volts. and I travel again through this 20 ohms minus plus. So it is minus 20 into 0.22. That is the current through this 20 ohms. So 20 into 0.22 is 4.4 volt. So 6 volt minus 4.4 volt is nothing but 1.6 volt. So VAB is 1.6 volt and RTH is 17.1 ohms. Let me draw the Thevenin's equivalent circuit here. This is 1.6 volt and this is 17.1 ohms. So the value of RL, which is connected here across AB now, has to be equal to, RL should be equal to 17.1 ohms. So to find the voltage across AB, students can even use voltage division rule, because this 10 volt, 10 ohms, 15 ohms branch, 25 ohms, 20 ohms branch, all are in parallel. This section, and this section, all are in parallel. So you can use voltage division rule to find out what is the voltage across 15 ohms and voltage division rule to find what is the voltage across 20 ohms. Let me do that also. Voltage across 15 ohms. Voltage across 15 ohms is equal to the total voltage 10 into 15 divided by, that is this 15 divided by 15 plus 10. 15 plus 10 is 25, which you will get it as 6 volts. So you see here this 6 volts voltage across this 15 ohms resistor you got even by voltage division rule. So voltage across 20 ohms is also similarly 10 volts into 20 divided by this branch now 20 divided by 20 plus 25, that is 45, which will be around 4.4 volt. So same, okay. So either you can use voltage division rule to find the voltage across 15 and 20, or you can find current and then multiply current with resistor to find voltage drop across 15 ohms and 20 ohms. So this is the final Thevenin's equivalent, where we have used maximum power transfer to find out the value of the load resistance. The load resistance value is equivalent to the source resistance or the Thevenin's resistance 17.1 ohms. So when this is equal to 17.1. If you would like to find the power dissipated in this particular resistance or current through this particular resistance, then let me mark this as load current. Load current is equal to 1.6 volts divided by 2 times 17.1 ohms, which will be around 0.05 amps. So power dissipated in the load resistance RL, that is 17.5 ohm, is I square, that is IL square into RL. So you have to square this and multiply it with RL, which you will get it as 0.04 watts. This is the power dissipated in the load resistance. So students, we will solve more problems in the coming videos.